section 2.9, we're taking a look at another type of number. Some of you have used them a couple of times along the way, and I said things like, we're not there yet. So we're going to look at complex numbers today. So to start with, we're going to talk about what an imaginary number is. The imaginary unit I is defined as either I squared is equal to -1 or I equals the square root of -1. So with that in mind, we're going to do some simplification with imaginary units. Everything that we work with in this section will be considered a complex number. So a complex number will have an I component, and it will typically also have a real number component. So you'll see a lot of things that might just look like, say, 5i, but you'll also see a lot of things that might look like, say, 3 plus 5i, and these are both considered complex numbers. So we have both of those types of numbers within our section here. Starting with, we're just going to take a look at items and how they would simplify or be rewritten using this definition over here. The idea that I is equal to the square root of -1. So in a very real sense, when we look at our square roots, we often are looking for, specifically with square roots, 2 items underneath the radical that match, and we bring them out once, right? So if we have 2 squared, like 2 is in there twice, we can bring out 1, 2. Agreed? Okay. When we have a negative, what we can do is we can bring the negative out, and when it comes out as a single imaginary unit, I. So this negative right here means that I'm going to have an I, and the 5, who does not have a pair, will remain underneath the radical. So this is I on the outside, square root of 5 still under. But we can have both of those pieces happening. So this negative, of course, will be brought out as a I. And the number 8 can be broken down. How can it break down? 2 and 4. Okay, so we'll do it that way first. And then 4 is 2 and 2. So it breaks down into 3 2's, right? So just like before, when we have square roots, if we're looking for 2 units that match, we have 2 2's here that match. So 1 2 will come out. We'll write it in front of the I, and there's still a lonely 2 left underneath the radical. Now, there's really nothing special about the fact that I put the 2 before the I. You could write it as I2 square root of 2. You don't usually see it written that way, but it's not wrong. There's also nothing written that says you have to have the I in front of the square root. You could put the I behind the square root. I would strongly advise you don't, because you don't want the I to ever look like it's actually under the square root, right? So I think by having it written in front, we eliminate the possibility of it accidentally looking like it's underneath. So that's where I'm going to suggest that you put it. On this one right here, we actually see imaginary radical pieces, right, where they're multiplied. So we want to be a little bit careful. What we're going to do is we're going to pull these i's out. Okay, so I have I square root of 3, and I have I square root of 12. Okay, once I've pulled them out, or even in the same step if it's okay with you to do so, you're welcome to group the i's together and to group the radicals together. Okay, so what do you get when you take I times I? Yeah, it's I squared. And then we have a property, we had one earlier back in chapter or unit 1, where we said if we have a square root times the square root, the property looked like this. It said the square root of A times the square root of B. This is for real numbers. This is equal to the square root of AB. Y'all remember that property? It doesn't work for addition. It works for multiplication and division. And so we have that property happening as long as A and B are real numbers. And so that's working for us right here. So this 3 right here and this 12 right here can go like that. While you're welcome to multiply the 3 times the 12, and in this case, it actually works out very nicely to give you 36. And then you can take the square root. You can also break it down from there. So on this one, let me show you a couple of options just because it does work out very nicely. If you were to multiply these, you'd have the square root of 36 like that. What's the square root of 36? 6. So this becomes just 6i. Generally speaking, we don't end up with a perfect square underneath there if we try to do that. And so it's often easier. You should say I squared. Sorry, I haven't gotten that on there. I missed it on all 3 pieces. Goodness gracious. I squared because there's 2 i's. So generally speaking, it works better to take the numbers and to break them down, right? 12 is 4 times 3, and 4 is 2 times 2. So we'd have 2 times 2 times 3 like this, and we'd look for pairs. So a pair of 2s comes out, and a pair of 3 comes out. So it still gets 6 coming out, but oftentimes we won't have everything coming out. So at this point, whichever direction we've come at this, we have 6i squared. Okay, so this is where we are right now. 6i squared is not simplified because I squared is equal to -1, right? That's a definition. I squared is equal to -1. So 6i squared is equal to 6 times -1, or simply -6. So when we multiply complex numbers, we don't always end up with a number at the end that still has an I in it. And this is an example of one where we would not. So it's a little bit weird. Any questions on that one? Okay, let's try one with division. So it's really tempting to sort of mush these together and put the division over the whole thing. And it actually would be okay in general on this particular one because of the way that these cancel. But generally speaking, when you're working with division or multiplication, it will be best for you to get them with the i's out first. So as we see this negative underneath here, I pull out an I. And as we see the negative underneath here, I pull out an I. Okay, that's the best place to start because sometimes things go askew. If on this one we had tried to just push these together immediately, we would have multiplied -3 times -12 and we would have gotten positive 36. And our answer would have been 6 when it really should be -6. So my suggestion is to just be careful with the i's and deal with them separately from the radical part of it. On this one, it actually works out really nice because the I and the I cancel, right? So that's actually a very friendly one, whereas on the other situation, it didn't happen that way. At this point where I have square root of 20 over square root of 2, we did have a property as well that said that I have square root of a over square root of b. This is the same thing as the square root of a over b, as long as the a and the b are real numbers, giving me real numbers of positives. So I can actually put this as square root of 20 over 2. So what is 20 divided by 2? 10. So square root of 10. And does square root of 10 simplify? No. 10 divides into 5 and 2, but there aren't any pairs, so the square root of 10 does not simplify. Again, notice there's no imaginary units left in it. Katie?
If there's a negative already outside the square root?
It just stays. So, like, let's say you had a negative square root of -2i over the square root of, I don't know, 3 or whatever. The negative on the outside just stays negative. This should not have had a 2i. I wanted to say 20, like that, like we had on the last one. The negative on the outside stays negative, and then the negative on the inside becomes the I on the outside. And then we'd still have the square root of 20 on top and the square root of 3 on bottom. So the negative on the outside just makes the problem negative. The next set of problems, you're going to feel like, well, those are really easy. So when we're working with adding and subtracting imaginary units, it works just like it did when we were adding and subtracting polynomials. Like terms get added, unlike terms don't. So on this problem, I have 2 minus 3i plus 6 plus 2i. So I combine like terms. Well, 2 and 6 are alike. What's 2 plus 6? 8. Negative 3i and positive 2i are alike. So what's negative 3i plus 2i? Negative 1i or simply negative I. And you're done. It just works like it did when we had the variable x or w or u or k or whatever inside of our problems. You combine the things that are alike. You don't combine the things that are not. When there's subtraction, as always, you need to make sure you distribute things. So it might be worth taking another step just to be careful. That's a 2. That's a terrible 2. Let's try that. I have negative 6 and I have positive 6i. And then we can do the same thing we did before. The constants are alike. Negative 4 and negative 6 are negative 10. My positive 2i and my positive 6i are alike. 2i plus 6i is 8i. And I'm done. So don't try to overcomplicate them. We're combining the pieces that are alike, and we're leaving alone the pieces that are the same. Cameron, you're looking confused. Okay, is there anything I can clarify?
Oh, no, it's the negative you distributed.
It did. So anytime there's a negative in front of the parentheses, a negative in front of the parentheses, that negative applies to each of the pieces inside. So the negative 6, and then the opposite of negative 6i would be positive 6i. Okay, so that's addition and subtraction. They work just like with polynomials. Multiplication also works quite similar. It has a caveat at the end that we have to pay attention to. But the initial part of it works the same, all right? We're simply multiplying. So on this one, the 5i is out of the parentheses, and it's being multiplied by 2 and by 3i, so we're going to distribute. So what is 5i times 2? 10i. And then in a very real sense, 5i times a positive 3i would give me 15i squared. Okay, that's what I would have done with polynomials. Nothing different. The part that's different comes in the end where you end up having an I squared. So when we get to the end of the problem and we have I squared, we have to remember that I squared equals negative 1. So we put that in at the end. So I have 10i plus 15 times negative 1, or you could just jump to the fact that that makes it negative 15. That would be okay. So I have 10i minus 15. Or if you prefer, you can write negative 15 plus 10i. Doesn't matter. Same thing. Okay, so the only difference for polynomials and this is that the I squared equals negative 1 at the end. When we're looking at number 8, we see a problem that involves distribution of binomials. So you might want to do FOIL. That's an acronym we have used before. So we do our first terms. 2 times 3 is 6. My outer terms, 2 times negative I is negative 2i. My inner terms, 2i times 3 is 6i. And then my last terms, 2i times negative I. Good, negative 2i squared. So there's two things that we need to make sure that we consolidate here. One is the fact that there are like terms, negative 2i and positive 6i. And the other is the fact that I squared is equal to negative 1. So we have 6, and then 2i, negative 2i and positive 6i is positive 4i. And then at the end, I have negative 2 times negative 1, since I squared is equal to negative 1. So 2 times negative 1 negative 2 times negative 1 would make that a positive 2 at the end, which means it combines with the 6 at the beginning, right? So I have 8 plus 4i, or you can write it as 4i plus 8. Okay. Addition, well, we did simplification with imaginary units, then we did addition, we did subtraction, we did multiplication, so the last thing we should do is division, right? Those are our 4 basic operations. Division with imaginary units actually doesn't look like division. It looks like what we did when we did division with square roots. Do you remember doing division with square roots? We had things that looked like, say, 3 over the square root of 2 plus 2, or something like that. And it was telling us that we needed to do what with that denominator? Do you remember? There was a key word.
Divide itself.
Not quite, but you're really close, Harrison. It's not flip it. Okay, so we didn't multiply it by itself. We multiplied it by its conjugate, right? So the conjugate kind of looked like the flip of what's on bottom, though. It's the same piece that's on bottom, it's just the wrong sign or the opposite sign in between them, okay? And what we're actually doing is something called rationalizing the denominator. That's the key phrase I was looking for, rationalizing the denominator. So we're going to be doing the same thing here and in exactly the same way. The conjugate here was square root of 2 minus 2. right? It was exactly the same thing, but the opposite sign, and if we did it to the bottom, we had to do it to the top. We're going to see that same thing happen here. We need the conjugate of 3 plus I, and I bet you can pretty much figure out what it has to be. Don't stare at me, just tell me. 3 minus I, thank you so much. Yes, it's the same thing with the opposite sign. And if I do it on the bottom, I'm going to do it on the top. Now what I want you to remember is that the reason that these were nice to multiply together is because the inner and the outer terms matched and eliminated each other. Right? This inner term is 2 square root 2. This outer term is negative 2 square root of 2. They add to 0. And it eliminated the imaginary units, or in that case, the radical units. Ours are going to do the same thing, but they're going to eliminate the imaginary units in the denominator. Okay? And we had a connection to this at another place as well. Do you remember when we talked about the difference of squares? The difference of squares formula said that if we were factoring a squared minus b squared, it factored into a pair of conjugates, a plus b and a minus b. Okay, so this relates directly to that as well. So when I have that denominator that's 3 plus I and 3 minus I very much can multiply it out in FOIL. That's okay. 3 times 3 is 9. In the inside I get positive, well, we'll do the outside first for patterns. On the outside I get negative 3i. On the inside I get positive 3i. And on the last I get negative I squared. But every single time I do this, because I've chosen to multiply by the conjugate, the inner and the outer terms cancel. Okay? I have some cancellation going on. And while I still have an I at the moment in the denominator, is the I going to be able to go away? It is, because what is I squared? Negative 1. Okay, so we'll finish out the denominator in a moment. Let's finish out our numerator first. So in my numerator, I do still have I typically. I'll distribute through here. So I have 2i times 3 gives me 6i. And 2i times negative I gives me negative 2i squared. So each of my locations right now where I have an I squared, I'm going to rewrite them as negative 1. So on the top, I have 6i minus 2 times negative 1. On the bottom, my inner and outer terms canceled, right there. So I have the 9, and I have the minus, and I squared is negative 1. So all of this gives me what? The part in the red? It's positive 2. Yeah? Negative 2 times negative 1 is positive 2. In the denominator, I have 9 what? What's after that? Plus 1. Whoops, plus 1. So on top, 6i plus 2. On bottom, what? 10. But, can reduce one more thing. What can I reduce, Harrison?
2, 6.
Yeah, so all of my numbers are even, right? They all divide by 2, so I can divide each of them by 2. So this one divide by 2 to give me 3, divide by 2 to give me 1, and divide by 2 to give me 5. So I end up with 3i plus 1 over 5. So these problems where we're rationalizing, they really do incorporate every other piece that we've done. They incorporate the simplification of the I squareds. They incorporate the conjugate that we've done in radicals, right? They have these things eliminating like we want them to do. We're combining like terms. We have, in fact, all the pieces. So if we're taking a look at number 10 then, what is it that we need to do? The same thing. So what will we be multiplying by, Isaiah? Do you know?
The bottom, the denominator, whatever it's called.
Okay, but not exactly the denominator.
The opposite.
The opposite sign. So I have 4 minus 2i. It's always by the conjugate of the denominator. 4 minus 2i. So let's just start with the top, so my spacing will work out a little bit nicer this time. I have the 2 minus I that has to FOIL with the 4 minus 2I. So my first terms, 2 times 4, are 8. My outer terms, 2 times negative 2I would be negative 4I. My inner terms, negative I times 4 would be another negative 4I. Those will not cancel generally. I have the last terms, which is negative I times negative 2I, which is what? Yeah, negative 2I squared. 4 pieces, that's my numerator. We're going to do the same thing with the denominator. The first terms, 4 times 4, give me 16. My inside, so yes.
On the top, would it be positive 2I squared?
On that one, it would be. Yep. Thanks for catching that. Yep. Negative times a negative, so a positive 2I squared. Thank you. All right, so my outer terms on the bottom is negative 8I, and my inner term is positive 8I. If you want to write them in, feel free to do so. If you want to not write them in because you see right away that they're going to cancel, then feel free to do so. Okay, but they will in fact cancel, not just combine, but completely add to 0. And then my last terms multiplied, positive 2I times negative 2I, give me,
Negative 4I squared?
yep, negative 4I squared. So while they didn't cancel, they do in fact combine in the middle on top, right? So I have an 8, I have negative 8I. And these I squareds will equal negative 1. So I have a positive 2 times negative 1. And on the bottom I had 16. And I have a negative 4 times negative 1. All right, so we have 8 minus 8I. And then I have minus 2 on top. And on bottom, I have 16 plus 4. So we'll combine the coefficients, the number of pieces that are alike. 8 and negative 2 gives me 6. So I have 6 minus 8I. On bottom, what do I have? 20. Am I done? No, but I'm so close. What's lacking? Reducing. They're all even again. I promise they're not always all even at this point. These just worked out that way. So yes, they happen to be all even. 6 divided by 2 is 3. 8 divided by 2 is 4. And 20 divided by 2 is 10. So I end up with 3 minus 4I over 10 for my final answer there. All right, so I'm going to keep this going that way in case we do have a couple people gone today, so that they're aware of a couple things. The first thing is we have a class on Tuesday next week. Okay, come Tuesday, but Thursday we're going to take a break. I got to be out of town, so we're just having class on Tuesday next week. Second thing is I have an extra credit opportunity for you. Okay, all ears. Here's what it is. You have received an invitation. They always word it that way. An invitation to participate in an evaluation for the class. Did you receive such an invitation inside of Canvas? Did it feel like an invitation? Not exactly. They never feel like invitations when I get them either to participate in a survey. Invitation to participate in a survey. I actually really would like your feedback. Now, if we get 100% participation for the class, then everybody gets bonus points. And I do realize that that is very not American. It's like a socialist, communist kind of like, but the problem is I can't see who did it and who didn't because it's protecting your anonymity. So this is when you turn on your neighbor and you say, did you do the survey? Did you do the survey? Did you do the survey? Because I want my extra credit. If you've already done it, you're done, you're good. Okay? Is that what you want to say? No?
I thought we were required to do that.
So it may have said required, but I mean, really? I would love for you to do it. A couple of things about it, though, just for like seriousness purposes. you can do whatever you want in it, and nobody will ever know it's you, and I understand that. But I actually use that as feedback on how to adjust my classes. So if you would take it seriously and give me like true feedback in a respectful way, because honestly, if I get feedback that's disrespectful, I usually disregard it as well. So feedback that tells me what worked, what was really good, things that you don't think worked well, things that you might suggest that might have worked better for you, that really helps me, and I do adjust and make things different based on that feedback for classes. We've changed this course specifically, intermediate algebra that you're taking, significantly based on student feedback. It used to look completely different. So please give me feedback. I really would like to hear your thoughts. And if we get 100% participation, you get 3 bonus points. That's what it is, 3 bonus points. Okay?